So in multivariable calculus, there are often a couple of ways to evaluate certain expressions or integrals, and you could consider them shortcuts, really. So let's look at a particular simplified version of a shortcut which will lead to what's called the divergence theorem. First of all, let's suppose that we're having a vector field, big F, with component functions fxy and gxy, and it's a vector field in the xy plane. And there's a region R in the xy plane whose boundary curve is C, as you see here. And let's say that curve is a piecewise smooth, positively oriented, simple and closed curve, and that f and g are continuous and have continuous first partial derivatives. Now suppose that the boundary curve C is traced out by the endpoint of a vector valued function we'll call r of t. And we have component functions x and y in terms of t, and t varies from a to b. And let's say that those component functions x and y have continuous first derivatives for those t values from a to b. So if all that criteria is met, we're going to encounter a very interesting trick or shortcut when it comes to an evaluation of an integral. First of all, to motivate that shortcut, let's verify that this outward unit normal vector c at any point is given by this expression. We'll call this the normal expression, outward unit normal vector. So if you look at this picture, here's a tangent vector pointing, of course, in the general direction of the orientation of curve C, positively oriented, and we have this unit normal vector, obviously orthogonal to that unit tangent vector. Well, in order to show very easily that this really is the expression for the unit normal vector, let's recall an expression for the unit tangent vector to the curve C. You recall a unit tangent vector t of t is simply you take the component functions of the position vector x prime t, y prime t, take their derivatives of those component functions, and you divide by the norm of r prime of t. It's interesting, when you dot that expression with n, okay, so here's the unit tangent expression, here's the alleged unit normal vector. When you dot those two things, notice what happens, right? You multiply the first component, so you get x prime, y prime over the norm of r prime squared. And I'm going to subtract, because we have a positive y prime of t and a negative x prime of t. I'm going to subtract y prime t, x prime t over the same norm of r prime t squared. Well, you'll notice that the numerators simply cancel out and you're left with zero scalar. And of course, what does that mean? That implies that these two vectors are indeed orthogonal to one another. And we could verify the representation of this outward unit normal vector by examining the possibilities of the signs of the components. So if you look at this particular diagram, what would be the sign of the components of the unit tangent vector? Well, it's going in the negative x direction, so the x component will be negative, and it's going in the positive y direction, it's going upward. So we would expect that y component to be positive. Well, what would the unit normal vector, what would its components be? Well, it looks like it's going in the positive x direction and positive y direction. And you'll note that that is captured by this expression. So we have y prime of t. Well, the y was positive from the unit tangent vector, so that means the y prime of t here for the normal is also positive. But in the picture, the x prime component of the unit tangent vector was negative. But if you take the negative of that in the unit normal expression, we get another positive component. Of course, the norms of the r primes are always going to be positive. So indeed, a unit tangent vector with a negative x component and a positive y component would imply a unit normal vector that has positive x and y components pointing outward, as you see in this diagram. So it all harmonizes and it works nicely with this picture. Now, again, we're trying to establish a neat shortcut which will then extend into the divergence theorem. You can recall that the evaluation theorem for line integrals allows us to express flux as so. So we have flux as the line integral positively oriented of the vector field f dot with the normal vector along that curve s ds. Okay, now if we express that in terms of t, we have f dot n of t times norm of r prime of t dt. Now how does that actually mean the same thing as this? Well, remember what r prime t dt really is. R prime is simply the component of vectors, a vector with components dx dt, dy dt. You're going to multiply that by dt. You have this dt hanging on the outside. So if you let those differentials interact, if you will, you're left with the vector dx dy, right? A vector that has dx and dy as components. So that represents r prime t dt. And if we take the norm of that, we just take the square root of the sum of the components squared. Well, that is exactly what we mean by the differential ds, so a little snippet of arc length along the boundary curve. So if we want to, again, express flux in parametric form, we have the parameter t involved. So we have, let's see, the vector field big F represented here with little f, little g, dotted with the unit normal vector, which we've already established in the previous slide. And we have hanging out here on the outside the norm of r prime of t dt. Now if you take a moment, you'll notice that if we make this dot product do its thing, if you will, and you have the r prime t dt on the outside, well, those r prime of t, the norm of the r prime of t's rather, will interact and cancel out. And you're left with this expression, which might be starting to look a little familiar. Let's see. If we perhaps see through the parameter t for a moment, just express things in terms of x and y, you have this, right? So we have f of xy dy, which is what y prime t dt is, minus g of xy dx, which is what x prime t dt is. Kind of looks familiar, right? It kind of looks like Green's theorem, but not quite. We know from Green's theorem, it looks like this, right? The evaluation of a line integral using Green's theorem, well, we usually have a plus in the middle here instead of a minus. And we're used to seeing the dx integral in the front and dy integral in the last part. And that's equal to a double integral over the region of, let's see, partial derivative of this second component g minus partial derivative of the first component f with respect to y, right? First one with respect to x, second with respect to y. Almost looking like this. So the question is, can I make this line integral obey the structure of adding instead of subtracting? And the answer is, of course you can. You just put the negative g of xy in the front. So again, how can the structure of Green's theorem be used to rewrite this integral? Simply put your negative g of xy dx integral in the front, plus the f of xy dy component. But now that's starting to look much the same as Green's theorem. In fact, we are accustomed to seeing the dx integral, the dx differential first and the dy differential second. So now all we got to do is apply the structure of Green's theorem. So Green's theorem says double integral partial of the second function g with respect to x. Well, that second function here, instead of being g, is f, but we still want to do that with respect to x. Minus, Green's theorem says, minus the first function with respect to y. Well, the first function here is, instead of little f, it's negative little g. So minus partial derivative of negative g with respect to y. Well, of course, that's going to turn into the double integral of the sum of partial derivative of f with respect to x plus partial derivative of g with respect to y. Which makes us think, now, looking at that expression, what do we call the sum of the partial derivatives of f with respect to x and g with respect to y when we're in a plane, in the xy plane? What do we call that? Well, that has been typically referred to as simply divergence, right? So if we look at that integram, this double integral, we see that this is the divergence of f. So this is an alternate form, if you will, of Green's theorem, right? Giving us another way to express flux. So we now bring it all together. We say, okay, if we wanted to express the flux using a line integral, well, that's the same thing as taking a double integral over the region that that curve encloses, double integral of the divergence of that vector field f. And oftentimes, evaluating this double integral could be a lot easier than trying to navigate through evaluation of a line integral. So again, what have we accomplished? This is the first shortcut we were trying to establish. We're saying that the outward flux of a vector field across a simple curve C is equal to the double integral of the divergence of the vector field over the region enclosed by that curve C, which we'll call region R. It's a pretty neat trick. Okay? So again, this trick can lead to another trick. You can actually extend this approach in 2 space, and you could take it to 3 space. So this form of Green's theorem can really be generalized to closed surfaces that are boundaries of finite solids. So we're going to take it to another dimension. And those finite solids can consist of finitely many smooth surfaces joined together at the edges. And these piecewise smooth surfaces can be assigned an inward orientation or an outward orientation. And each piece of the surface is orientable, and oriented pieces will fit together in such a way that the entire surface can be assigned an orientation. With all that said, if all that criteria is met and you have a definite outward orientation for this solid, then you can use this trick in 3 space. And that trick in 3 space is called the divergence theorem. But I'd like you to think about the simplified case in 2 space, where we were taking a line integral instead of evaluating the flux by f dot n over that line integral structure. Use the double integral over the region of the divergence. If you think in terms of that simple case, that simple diagram in 2 space, it'll probably help you better appreciate and better grasp what's going on with the divergence theorem in 3 space. So anyway, here we go. The divergence theorem says let G this time be a solid whose surface sigma is oriented outward. And we have big F being that vector field, having continuous first partial derivatives for its component functions on some open set containing G. And if n, again, is the outward unit normal vector, then we can say that the double integral over the surface, f dot n ds, is really equal to the triple integral over the region that that surface is enclosing, the triple integral of the divergence of f over that solid. Again, this theorem states that the outward flux of a vector field across a closed surface is equal to the triple integral of the divergence over the region enclosed by that surface. So instead of going about figuring out the flux of a vector field across that surface with a surface integral, we can actually evaluate a triple integral of the divergence over the region that's enclosed by that surface. And a lot of times that could be a lot easier. Let's take an example. Let's have G be the solid bounded by this paraboloid. Z equals 4 minus x squared minus y squared in the xy plane is the lower boundary. Let's find the flux of the vector field F, which is components x cubed, y cubed, z cubed, over the outward oriented surface sigma of the paraboloid. Now, if you think about it, if you want to evaluate this using flux integrals over surface integrals, right? Instead of going through all that trouble, we could use instead one triple integral. So instead of evaluating 2 flux integrals separately for each portion of this surface, right? We have the paraboloid lateral surface, if you will, and we also have this bottom circular surface of the paraboloid intersecting with the xy plane. But instead of evaluating 2 flux integrals separately over each portion of that surface, we're going to evaluate one triple integral of the divergence of F and get the answer for the flux of this vector field. So again, we now know from the divergence theorem that the double integral over the surface f dot n ds is equal to the triple integral of the divergence of F. So let's see, triple integral divergence of F. Well, F was x cubed, y cubed, z cubed. Divergence, just take the partial derivatives with respect to x, y, and z of each component, and here's where we get the divergence, right here in this integrand. 3x squared plus 3y squared plus 3z squared. Now, we don't have a spherical shape here. If you were thinking spherical, actually that's not the best way to go. Instead, we're going to use cylindrical coordinates in this particular example. So obviously you see the 3 could be factored outside the triple integral, and now we're going to change this all into cylindrical coordinates. So if we factor out the 3, we'll be left with x squared plus y squared, which we know is r squared. And we have that z squared, which is part of the cylindrical coordinate system. We just got to remember to put r dz dr d theta to have the appropriate evaluation. And let's think now. Z goes from all the way from 0 to whatever portion of this top part of the paraboloid we're going to, which is, of course, z equals 4 minus r squared, right? Z equals 4 minus x squared minus y squared, but that can be expressed as z equals 4 minus r squared. So that's where we get these limits of integration for the z's. When we look for r, let's see, r is the distance from the pole, well, that can go as little as 0 all the way to the outward distance of 2. So r goes from 0 to 2. And if we want to go all the way around, we need from theta to go from 0 to 2 pi. And really the rest of this problem is simply an evaluation of a cylindrical coordinate triple integral, which no doubt you have much experience doing already. So let's see, let's just knock out the algebra here really quickly. If we distribute that r, we get r cubed and z squared times r. Now we're going to integrate that with respect to z, so we get r cubed z plus r z cubed over 3. And we're going to now put in our limits of integration. Z goes from 0 to 4 minus r squared, which of course just boils down to putting the 4 minus r squared for z in each piece. And we have this expression. And with, let's see, a little algebra expanding that a bit. If I did all my algebra correctly, and now we're going to finally put in 0, which let's just all go to 0, and just really substituting 2 is what we're doing. And we would get 16, and then we're going to take that from 0 to 2 pi with theta, so it's 3 times 16 theta, as theta goes from 0 to 2 pi, which is 3 times 32 pi, or a final answer of 96 pi. But again, the whole point of this is to help you appreciate the shortcut and why it works. Instead of having to go through each surface to evaluating the flux across each surface, we could just do one triple integral and get the same evaluation. So it's a neat shortcut. And soon we'll talk about doing the net flux of the curl. I'm so stoked about that next video coming up.